Yesterday we looked at radians and degrees in measuring an angle. So if we looked at an angle like we have here, where our unit circle has a radius of 1, and that this disk is our central angle, if we're in radians. So what we're going to look at today is continuing to deal with this arc length, but also look at this kind of section of the circle. What's the area of this kind of wedge shape, this pie shape? So we're going to have two formulas. To find the arc length, and the arc length S is this edge of this pie shape. That is just equal to R times theta, where R is our radius. In the unit circle, R was 1, as we showed back here. They were equal. But if our radius is something different, we have to multiply by the length of that radius. We also have the area of this sector of a circle, A, and in this case our area is 1/2 R squared theta. The important thing is in both of these, theta has to be in radians. We can't do it in degrees. Theta has to be in radians. So let's look at an example. Find the arc length and area of a sector. Our radius is 15. Our radius is 15, and our central angle is pi over 6. So our arc length is S. Our area is A. And if we go back and look at our formula, it's just R, 15, times theta, which is pi over 6. And if we multiply that, 15 times pi divided by 6, we get 7.85. Our area is 1/2 R squared times pi over 6. So if we take 1/2 times pi over 6 times 15 squared, we get 58.90. Whatever our units, this S would be just like, let's say this is 15 meters, 15 centimeters. This would be meters. This would be meters squared. Okay. So there's how we can use our formulas. Now, let's go the other way. Find the arc length and area of the sector if R is 3.5 and theta is pi over 12. So our S is just R times theta. And our area is 1/2 R squared times theta. Give you a second, try plugging both of those into your calculator and see how you do. The answers you should get, your arc length is 0.916 and our area is 1.60. So those are just using our formulas. Let's change it up a little bit. The sector of a circle has an area of 26.25 and a central angle of 2.5 radians. Find the radius and the arc length. Well, we know this central angle here is 2.1. Not sure why I just wrote 2.6. We know it's 2.1. And we know our area is 26.25. So our area is 1/2 R squared theta. So this is 26.25, 1/2 R squared 2.1. So I'm going to multiply both sides by 2, divide by 2.1, and I get my r squared is 25, so my r is 5. Now to find my arc length, I take r times theta in radians, and I get 10.5 centimeters. I should say that my r, my radius, is 5 centimeters. So that's using our formulas. Now we want to look at a few other definitions. First is linear displacement. Now, they kind of define this as distance traveled, and you can think of it as distance traveled, but another way to think about it is not distance traveled, it's where you finish minus where you start. So what do I mean by that? Well, if you think of linear displacement, imagine track for a second, and you ran the 400 meters, and you went all the way around the track. Where you finished minus where you started, your linear displacement would be 0, because you're the same place you started. Now, if you ran the 100 meters and you went from the start line to the finish line, that's a straight line. That would be 200 meters. If you imagine for a second, here's our track, and you ran the 200 meters, and you went from here and you finished there, we could think of our displacement as where you finished minus where you started, and if you measured it, it would almost be in a straight line. So usually we talk about this in a straight line, but for us, we're just going to think of linear displacement as, to keep it simple, as distance traveled. How far did you go? The distance you traveled. Angular displacement is the angle of rotation. So for example, if I started here and I rotated this far, my angular displacement is pi over 2. I went 90 degrees. That's angular displacement. How far you spun, so to speak. It wouldn't make a difference if you were here and you went to there, or if you went from here and you went to there. Our angular displacement would be the same. The linear displacement would be different. This point at point 1 is going a shorter distance than this point out here at point 2 is going a longer distance. So that's the difference between the two. So, a wheel with radius 10 centimeters spins 4 times. What's the angular displacement in radians? Well, the radius doesn't really matter for angular displacement. If we think of our angle, it spins 4 times. It goes around once, twice, 3 times, 4 times. So what's my angular displacement? Well, 4 times 2 pi each time around, and I get 8 pi radians. That is my angular displacement. What's my linear displacement? Well, if we think of a wheel and it spins 4 times, there's 2 ways we can think about that. One, we can think of circumference, 2 pi r, which is 2 pi times 10. Well, that's 20 pi times my 4 revolutions, and I get 80 pi. That's kind of not really using what we've just been talking about. Let's use our formula. S equals r theta. My arc length, my angle, my radius is 10. My angle is 8 pi, so I get 80 pi. I get the same answer both ways. Whether I just figure it out using my circumference, or whether I figure it out using our formula for our arc length that we used earlier. Now, angular displacement is this distance traveled. Linear displacement is distance traveled. Angular displacement is angle of rotation. We now want to look at linear and angular velocity. And the only difference by velocity is you divide by the time. Think about it, if you go 120 miles in 2 hours, your velocity is 60 miles per hour. That's all it is. So we're adding a time to how fast we're spinning or how far we're going. So our wheel of radius 10 spins 4 times in 20 seconds. What's the angular velocity? Well, we just found on the earlier problem, our angular displacement was 80 pi. Now, we divide that by our time of 20 seconds, and we get 4 pi centimeters per second. Our linear velocity, I'm sorry, that's the right, I used the wrong, yeah, 8 pi, sorry. Let's try it again. It's not 80, it was 8 pi. So, if I divide, this is going to be 2/5 pi. That's 2/5 radians per second. This should not say centimeters. That should be radians. If we want to find our linear velocity, that is the linear displacement over time. And we found this before to be 80 pi over 20. So this is 40, I can't divide here. That is 4 pi centimeters per second. Linear is how fast you're going in the line. Angular displacement is how fast you're spinning. So a disc spins at 1200 RPMs. What's the angular velocity in radians per second? All right. So 1200 RPMs. That is 1200 revolutions or rotations or whatever you want to think about it. I'm going to say rotations per minute. So use a little simplifying here. If you've taken chemistry, this will make sense. One rotation is 2 pi radians. Rotations cancel. 1 minute is 60 seconds. So the minutes cancel. So if we take 1200 times 2 divided by 60, we get 40 pi radians per second. So that's our angular velocity. Now if the diameter is 4 inches, notice the diameter does not affect angular velocity, because angular velocity is just how fast something's spinning. It doesn't affect the distance with the radius. Find the distance at a point at the outer edge travels in 1 minute. So our S is R times theta. Well, R is 4. Now, what is our theta? What's our angle? Well, if we do 40 pi radians per second, okay, or we can look at about this in terms of our minutes. I'm going to do it in seconds first. 40 pi radians per second. If I take 40 pi radians per second, 60 seconds is 1 minute. That gives me 2,400 pi radians per minute. So that's my angle. So I get 9,600 pi inches. That is how far I go per minute. Now, if the distance is a point 2 inches from the center, all that changes is I get a 2 instead of a 4, and I would get 4,800 pi inches. So what we're looking at is as something spins, as a wheel spins. Let's look at the shape here. As a tire spins, first off, if you're a point here and the tire spins, how far did you move? That theta. That is our angular displacement, or our angular velocity. How fast did you do it? If we want to find linear, we now want to say, what's the distance here in red that you actually traveled from this spot to this spot? And that depends on the radius, whether or not you are some distance from the center or whether or not you were on the edge. If you look at the red and the green, those would have different radiuses. They would have different angular displacements, angular velocity, but they would have the same different linear displacements, linear velocities, but they would have the same angular velocities or angular displacements because they're moving in the same angle in a certain time. We'll skip that one. Homework, sectors of circles.